faster than light communication and travel refer to the propagation of information or matter faster than the speed of light. Under the special theory of relativity, a particle with subluminal velocity needs infinite energy to accelerate to the speed of light, although special relativity does not forbid the existence of particles that travel faster than light at all times. On the other hand, what some physicists refer to as apparent, or effective FTL depends on the hypothesis that unusually distorted regions of spacetime might permit matter to reach distant locations in less time than light could in normal or undistorted spacetime. Although according to current theories matter is still required to travel subluminally with respect to the locally distorted spacetime region, apparent FTL is not excluded by general relativity. Examples of FTL proposals are the Alcubierre drive and the traversable wormhole, although their physical plausibility is uncertain. FTL travel of non-information. In the context of this article, FTL is the transmission of information or matter faster than c, a constant equal to the speed of light in a vacuum, which is 299,792,458 meters per second or about 186,282.4 miles per second. This is not quite the same as traveling faster than light, since some processes propagate faster than c, but cannot carry information. Light travels at speed cn when not in a vacuum but traveling through a medium with refractive index equals n, and in some materials other particles can travel faster than cn, leading to Cherenkov radiation. Neither of these phenomena violates special relativity or creates problems with causality, and thus neither qualifies as FTL as described here. In the following examples, certain influences may appear to travel faster than light, but they do not convey energy or information faster than light, so they do not violate special relativity. Daily sky motion. For an Earth-bound observer, objects in the sky complete one revolution around the Earth in one day. Proxima Centauri, which is the nearest star outside the Solar System, is about 4 light-years away. On a geostationary view, Proxima Centauri has a speed many times greater than c, as the rim speed of an object moving in a circle is a product of the radius and angular speed. It is also possible on a geostatic view for objects such as comets to vary their speed from subluminal to superluminal and vice versa simply because the distance from the Earth varies. Comets may have orbits which take them out to more than 1000 AU. The circumference of a circle with a radius of 1000 AU is greater than 1 light day. In other words, a comet at such a distance is superluminal in a geostatic, and therefore non-inertial, frame. Light spots and shadows. If a laser is swept across a distant object, the spot of laser light can easily be made to move across the object at a speed greater than c. Similarly, a shadow projected onto a distant object can be made to move across the object faster than c. In neither case does the light travel from the source to the object faster than c, nor does any information travel faster than light. Apparent FTL propagation of static field effects. Since there is no retardation of the apparent position of the source of a gravitational or electric static field when the source moves with constant velocity, the static field effect may seem at first glance to be transmitted faster than the speed of light. However, uniform motion of the static source may be removed with a change in reference frame, causing the direction of the static field to change immediately, at all distances. This is not a change of position which propagates, and thus this change cannot be used to transmit information from the source. No information or matter can be FTL transmitted or propagated from source to receiver-observer by an electromagnetic field. Closing speeds, the rate at which two objects in motion in a single frame of reference get closer together is called the mutual or closing speed. This may approach twice the speed of light, as in the case of two particles traveling at close to the speed of light in opposite directions with respect to the reference frame. Imagine two fast-moving particles approaching each other from opposite sides of a particle accelerator of the collider type. The closing speed would be the rate at which the distance between the two particles is decreasing. From the point of view of an observer standing at rest relative to the accelerator, this rate will be slightly less than twice the speed of light. Special relativity does not prohibit this. it tells us that it is wrong to use Galilean relativity to compute the velocity of one of the particles, as would be measured by an observer traveling alongside the other particle. That is, special relativity gives the right formula for computing such relative velocity. It is instructive to compute the relative velocity of particles moving at v in an accelerator frame, which corresponds to the closing speed of 2v, c. Expressing the speeds in units of c, I squared equals vc. Proper speeds: if a spaceship travels to a planet 1 light-year away from Earth at high speed, the time taken to reach that planet could be less than 1 year as measured by the traveler's clock. The value obtained by dividing the distance traveled, as determined in the Earth's frame, by the time taken, measured by the traveler's clock, is known as a proper speed or a proper velocity. There is no limit on the value of a proper speed, as a proper speed does not represent a speed measured in a single inertial frame. A light signal that left the Earth at the same time as the traveler would always get to the destination before the traveler. How far can one travel from the Earth? Since one might not travel faster than light, one might conclude that a human can never travel further from the Earth than 40 light-years if the traveler is active between the age of 20 and 60. A traveler would then never be able to reach more than the very few star systems which exist within the limit of 20 to 40 light-years from the Earth. This is a mistaken conclusion. Because of time dilation, the traveler can travel thousands of light-years during their 40 active years. If the spaceship accelerates at a constant 1 ag, it will, after 354 days, reach speeds a little under the speed of light, and time dilation will increase their lifespan to thousands of Earth years, seen from the reference system of the Solar System, but the traveler's subjective lifespan will not thereby change. If the traveler returns to the Earth, they will land thousands of years into the future. Their speed will not be seen as higher than the speed of light by observers on Earth, and the traveler will not measure their speed as being higher than the speed of light, but will see a length contraction of the universe in their direction of travel. And as the traveler turns around to return, the Earth will seem to experience much more time than the traveler does. So, although their speed cannot exceed c, the fall velocity can be much greater than c. This is seen in statistical studies of muons traveling much further than c times their half-life, if traveling close to c. Phase velocities above c, the phase velocity of an electromagnetic wave, when traveling through a medium, can routinely exceed c, the vacuum velocity of light. For example, this occurs in most glasses at X-ray frequencies. However, the phase velocity of a wave corresponds to the propagation speed of a theoretical single-frequency component of the wave at that frequency. Such a wave component must be infinite in extent and of constant amplitude, and so cannot convey any information. Thus a phase velocity above c does not imply the propagation of signals with a velocity above c. Group velocities above c, the group velocity of a wave may also exceed c in some circumstances. In such cases, which typically at the same time involve rapid attenuation of the intensity, the maximum of the envelope of a pulse may travel with a velocity above c. However, even this situation does not imply the propagation of signals with a velocity above c, even though one may be tempted to associate pulse maxima with signals. The latter association has been shown to be misleading, basically because the information on the arrival of a pulse can be obtained before the pulse maximum arrives. For example, if some mechanism allows the full transmission of the leading part of a pulse while strongly attenuating the pulse maximum and everything behind, the pulse maximum is effectively shifted forward in time, while the information on the pulse does not come faster than c without this effect. Universal expansion. The expansion of the universe causes distant galaxies to recede from us faster than the speed of light, if proper distance and cosmological time are used to calculate the speeds of these galaxies. However, in general relativity, velocity is a local notion, so velocity calculated using moving coordinates does not have any simple relation to velocity calculated locally. Rules that apply to relative velocities in special relativity, such as the rule that relative velocities cannot increase past the speed of light, do not apply to relative velocities in moving coordinates, which are often described in terms of the expansion of space between galaxies. This expansion rate is thought to have been at its peak during the inflationary epoch thought to have occurred in a tiny fraction of the second after the Big Bang, when the universe may have rapidly expanded by a factor of around 1020 to 1030. There are many galaxies visible in telescopes with redshift numbers of 1.4 or higher. All of these are currently traveling away from us at speeds greater than the speed of light. Because the Hubble parameter is decreasing with time, there can actually be cases where a galaxy that is receding from us faster than light does manage to emit a signal which reaches us eventually. However, because the expansion of the universe is accelerating, it is projected that most galaxies will eventually cross a type of cosmological event horizon where any light they emit past that point will never be able to reach us at any time in the infinite future, because the light never reaches a point where its peculiar velocity towards us exceeds the expansion velocity away from us. The current distance to this cosmological event horizon is about 16 billion light-years, meaning that a signal from an event happening at present would eventually be able to reach us in the future if the event was less than 16 billion light-years away, but the signal would never reach us if the event was more than 16 billion light-years away. Astronomical observations. Apparent superluminal motion is observed in many radio galaxies, blazars, quasars and recently also in microquasars. The effect was predicted before it was observed by Martin Rees and can be explained as an optical illusion caused by the object partly moving in the direction of the observer, when the speed calculations assume it does not. The phenomenon does not contradict the theory of special relativity. Interestingly, corrected calculations show these objects have velocities close to the speed of light. They are the first examples of large amounts of mass moving at close to the speed of light. Earth-bound laboratories have only been able to accelerate small numbers of elementary particles to such speeds. Quantum mechanics. Certain phenomena in quantum mechanics, such as quantum entanglement, might give the superficial impression of allowing communication of information faster than light. According to the no-communication theorem, these phenomena do not allow true communication. They only let two observers in different locations see the same system simultaneously, without any way of controlling what either sees. Wave function collapse can be viewed as an epiphenomenon of quantum coherence, which in turn is nothing more than an effect of the underlying local time evolution of the wave function of a system and all of its environment. Since the underlying behavior doesn't violate local causality or allow FTL, it follows that neither does the additional effect of wave function collapse, whether real or apparent. The uncertainty principle implies that individual photons may travel for short distances at speeds somewhat faster than c, even in a vacuum. This possibility must be taken into account when enumerating Feynman diagrams for a particle interaction. However, it was shown in 2011 that a single photon may not travel faster than c. In quantum mechanics, virtual particles may travel faster than light, and this phenomenon is related to the fact that static field effects may travel faster than light. However, macroscopically these fluctuations average out, so that photons do travel in straight lines over long distances, and they do travel at the speed of light on average. Therefore, this does not imply the possibility of superluminal information transmission. There have been various reports in the popular press of experiments on faster-than-light transmission in optics, most often in the context of a kind of quantum tunneling phenomenon. Usually, such reports deal with a phase velocity or group velocity faster than the vacuum velocity of light. However, as stated above, a superluminal phase velocity cannot be used for faster-than-light transmission of information. There has sometimes been confusion concerning the latter point. Additionally, a channel that permits such propagation cannot be laid out faster than the speed of light. Quantum teleportation transmits quantum information at whatever speed is used to transmit the same amount of classical information, likely the speed of light. This quantum information may theoretically be used in ways that classical information cannot, such as in quantum computations involving quantum information only available to the recipient. Hartman Effect. The Hartman effect is the tunneling effect through a barrier where the tunneling time tends to a constant for large barriers. This was first described by Thomas Hartman in 1962. This could, for instance, be the gap between two prisms. When the prisms are in contact, the light passes straight through, but when there is a gap, the light is refracted. There is a non-zero probability that the photon will tunnel across the gap rather than follow the refracted path. For large gaps between the prisms, the tunneling time approaches a constant and thus the photons appear to have crossed with the superluminal speed. However, an analysis by Herbert G. Winfall from the University of Michigan suggests that the Hartman effect cannot actually be used to violate relativity by transmitting signals faster than c, because the tunneling time should not be linked to a velocity since evanescent waves do not propagate. The evanescent waves in the Hartman effect are due to virtual particles and a non-propagating static field, as mentioned in the sections above for gravity and electromagnetism. Casimir effect. In physics, the Casimir effect or Casimir polar force is a physical force exerted between separate objects due to resonance of vacuum energy and the intervening space between the objects. This is sometimes described in terms of virtual particles interacting with the objects, owing to the mathematical form of one possible way of calculating the strength of the effect. Because the strength of the force falls off rapidly with distance, it is only measurable when the distance between the objects is extremely small. Because the effect is due to virtual particles mediating a static field effect, it is subject to the comments about static fields discussed above. Epr Paradox. The Epr paradox refers to a famous thought experiment of Einstein, Podolsky and Rosen that was realized experimentally for the first time by Alan Aspect in 1981 and 1982 in the Aspect experiment. In this experiment, the measurement of the state of one of the quantum systems of an entangled pair apparently instantaneously forces the other system to be measured in the complementary state. However, no information can be transmitted this way. The answer to whether or not the measurement actually affects the other quantum system comes down to which interpretation of quantum mechanics one subscribes to. An experiment performed in 1997 by Nicholas Gissin at the University of Geneva has demonstrated non-local quantum correlations between particles separated by over 10 kilometers. But as noted earlier, the non-local correlations seen in entanglement cannot actually be used to transmit classical information faster than light, so that relativistic causality is preserved. See no communication theorem for further information. A 2008 quantum physics experiment also performed by Nicholas Gissin and his colleagues in Geneva, Switzerland has determined that in any hypothetical non-local hidden variables theory the speed of the quantum non-local connection is at least 10,000 times the speed of light. Delayed choice quantum eraser. Delayed choice quantum eraser is a version of the Epr paradox in which the observation or not of interference after the passage of a photon through a double-slit experiment depends on the conditions of observation of a second photon entangled with the first. The characteristic of this experiment is that the observation of the second photon can take place at a later time than the observation of the first photon, which may give the impression that the measurement of the later photons retroactively determines whether the earlier photons show interference or not, although the interference pattern can only be seen by correlating the measurements of both members of every pair and so it can't be observed until both photons have been measured, ensuring that an experimenter watching only the photons going through the slit does not obtain information about the other photons in an FTL or backwards in time manner. FTL communication possibility, faster-than-light communication is, by Einstein's theory of relativity, equivalent to time travel. According to Einstein's theory of special relativity, what we measure as the speed of light in a vacuum is actually the fundamental physical constant c. This means that all inertial observers, regardless of their relative velocity, will always measure zero-mass particles such as photons traveling at c in a vacuum. This result means that measurements of time and velocity in different frames are no longer related simply by constant shifts, but are instead related by Poincare-Copyright transformations. These transformations have important implications. The relativistic momentum of a massive particle would increase with speed in such a way that at the speed of light an object would have infinite momentum. To accelerate an object of non-zero rest mass to c would require infinite time with any finite acceleration, or infinite acceleration for a finite amount of time. Either way, such acceleration requires infinite energy. Some observers with sublight relative motion will disagree about which occurs first of any two events that are separated by a space-like interval. In other words, any travel that is faster than light will be seen as traveling backwards in time in some other, equally valid, frames of reference, or need to assume the speculative hypothesis of possible Lorentz violations at a presently unobserved scale. Therefore any theory which permits true FTL also has to cope with time travel and all its associated paradoxes, or else to assume the Lorentz invariance to be a symmetry of thermodynamical statistical nature. In special relativity the coordinate speed of light is only guaranteed to be c in an inertial frame. In a non-inertial frame the coordinate speed may be different from c. In general relativity no coordinate system on a large region of curved spacetime is inertial, so it's permissible to use a global coordinate system where objects travel faster than c, but in the local neighborhood of any point in curved spacetime we can define a local inertial frame, and the local speed of light will be c in this frame, with massive objects moving through this local neighborhood always having a speed less than c in the local inertial frame. Justifications: faster light. Raymond Y. Chae was first to measure the quantum tunneling time, which was found to be between 1.5 to 1.7 times the speed of light. Einstein's equations of special relativity postulate that the speed of light in a vacuum is invariant in inertial frames. That is, it will be the same from any frame of reference moving at a constant speed. The equations do not specify any particular value for the speed of the light, which is an experimentally determined quantity for a fixed unit of length. Since 1983, the SI unit of length has been defined using the speed of light. The experimental determination has been made in vacuum. However, the vacuum we know is not the only possible vacuum which can exist. The vacuum has energy associated with it, unsurprisingly called the vacuum energy. This vacuum energy can perhaps be changed in certain cases. When vacuum energy is lowered, light itself has been predicted to go faster than the standard value c. This is known as the Scarnist effect. Such a vacuum can be produced by bringing two perfectly smooth metal plates together at near atomic diameter spacing. It is called a Casimir vacuum. Calculations imply that light will go faster in such a vacuum by a minuscule amount. A photon traveling between two plates that are 1 micrometer apart would increase the photon speed by only about 1 part in 1036. Accordingly there has as yet been no experimental verification of the prediction. A recent analysis argued that the Scarnist effect cannot be used to send information backwards in time with a single set of plates since the plate's rest frame would define a preferred frame for FTL signaling. However, with multiple pairs of plates in motion relative to one another the authors noted that they had no arguments that could guarantee the total absence of causality violations, and invoked Hawking's speculative chronology protection conjecture which suggests that feedback loops of virtual particles would create uncontrollable singularities in the renormalized quantum stress energy on the boundary of any potential time machine, and thus would require a theory of quantum gravity to fully analyze. Other authors argue that Scarnist's original analysis which seemed to show the possibility of faster than c signals involved approximations which may be incorrect, so that it is not clear whether this effect could actually increase signal speed at all. The physicists Gerwin Korter-Ntillon Nimtz and Alphonse Stahlhofen, of the University of Cologne, claim to have violated relativity experimentally by transmitting photons faster than the speed of light. They say they have conducted an experiment in which microwave photons relatively low-energy packets of light traveled instantaneously between a pair of prisms that had been moved up to 3 ft apart. Their experiment involved an optical phenomenon known as evanescent modes, and they claim that since evanescent modes have an imaginary wave number, they represent a mathematical analogy to quantum tunneling. Nimtz has also claimed that evanescent modes are not fully describable by the Maxwell equations and quantum mechanics have to be taken into consideration. Other scientists such as Herbert G. Winfall and Robert Helling have argued that in fact there is nothing quantum mechanical about Nimtz's experiments, and that the results can be fully predicted by the equations of classical electromagnetism. Nimtz told New Scientist magazine, "For the time being, this is the only violation of special relativity that I know of." However, other physicists say that this phenomenon does not allow information to be transmitted faster than light. Ephraim Steinberg, a quantum optics expert at the University of Toronto, Canada, uses the analogy of a train traveling from Chicago to New York, but dropping off train cars at each station along the way, so that the center of the ever-shrinking main train moves forward at each stop. In this way, the speed of the center of the train exceeds the speed of any of the individual cars. Herbert G. Winfall argues that the train analogy is a variant of the reshaping argument for superluminal tunneling velocities, but he goes on to say that this argument is not actually supported by experimental simulations, which actually show that the transmitted pulse has the same length and shape as the incident pulse. Instead, Winfall argues that the group delay in tunneling is not actually the transit time for the pulse, but is instead the lifetime of the energy stored in the standing wave which forms inside the barrier. Since the stored energy in the barrier is less than the energy stored in a barrier-free region of the same length due to destructive interference, the group delay for the energy to escape the barrier region is shorter than it would be in free space, which according to Winfall is the explanation for apparently superluminal tunneling. A number of authors have published papers disputing Nymtz's claim that Einstein causality is violated by his experiments, and there are many other papers in the literature discussing why quantum tunneling is not thought to violate causality. It was later claimed by the Keller group in Switzerland that particle tunneling does indeed occur in zero real time. Their tests involved tunneling electrons, where the group argued a relativistic prediction for tunneling time should be 500 to 600 attoseconds of a second. All that could be measured was 24 attoseconds, which is the limit of the test accuracy. Again, though, other physicists believe that tunneling experiments in which particles appear to spend anomalously short times inside the barrier are in fact fully compatible with relativity, although there is disagreement about whether the explanation involves reshaping of the wave packet or other effects. Give up relativity. Because of the strong empirical support for special relativity, any modifications to it must necessarily be quite subtle and difficult to measure. The best-known attempt is doubly special relativity, which posits that the Planck length is also the same in all reference frames, and is associated with the work of Giovanni Amelino Camiglia and Joe Pound Omaguajo. One consequence of this theory is a variable speed of light, where photon speed would vary with energy, and some zero-mass particles might possibly travel faster than c. However, even if this theory is accurate, it is still very unclear whether it would allow information to be communicated, and appears not in any case to allow massive particles to exceed c. There are speculative theories that claim inertia is produced by the combined mass of the universe, which implies that the rest frame of the universe might be preferred by conventional measurements of natural law. If confirmed, this would imply special relativity as an approximation to a more general theory, but since the relevant comparison would be outside the observable universe, it is difficult to imagine experiments to test this hypothesis. Spacetime distortion. Although the theory of special relativity forbids objects to have a relative velocity greater than light speed, and general relativity reduces to special relativity in a local sense, general relativity does allow the space between distant objects to expand in such a way that they have a recession velocity, which exceeds the speed of light, and it is thought that galaxies which are at a distance of more than about 14 billion light-years from us today have a recession velocity which is faster than light. Miguel Alcubierre theorized that it would be possible to create an Alcubierre drive, in which a ship would be enclosed in a warp bubble, where the space at the front of the bubble is rapidly contracting and the space at the back is rapidly expanding, with the result that the bubble can reach a distant destination much faster than a light beam moving outside the bubble, but without objects inside the bubble locally traveling faster than light. However, several objections raised against the Alcubierre drive appear to rule out the possibility of actually using it in any practical fashion. Another possibility predicted by general relativity is the traversable wormhole, which could create a shortcut between arbitrarily distant points in space. As with the Alcubierre drive, travelers moving through the wormhole would not locally move faster than light which travels through the wormhole alongside them, but they would be able to reach their destination faster than light traveling outside the wormhole. Dr. Gerald Cleaver, Associate Professor of Physics at Baylor University, and Richard Abussy, a Baylor graduate student, theorized that by manipulating the extra-spatial dimensions of string theory around a spaceship with an extremely large amount of energy, it would create a bubble that could cause the ship to travel faster than the speed of light. To create this bubble, the physicists believe manipulating the 10th spatial dimension would alter the dark energy in 3 large spatial dimensions: height, width and length. Cleaver said positive dark energy is currently responsible for speeding up the expansion rate of our universe as time moves on. Haem Theory, in 1977, a paper on Haem theory theorized that it may be possible to travel faster than light by using magnetic fields to enter a higher dimensional space. MHSC quantized inertia. A new theory has been proposed that modifies inertia by assuming it is due to Unruh radiation subject to a Hubble-scale Casimir effect. MHSC predicts a minimum possible acceleration even at light speed, implying that this speed can be exceeded. Lorentz symmetry violation. The possibility that Lorentz symmetry may be violated has been seriously considered in the last 2 decades, particularly after the development of a realistic effective field theory that describes this possible violation, the so-called Standard Model extension. This general framework has allowed experimental searches by ultra-high-energy cosmic ray experiments and a wide variety of experiments in gravity, electrons, protons, neutrons, neutrinos, mesons, and photons. The breaking of rotation and boost invariance causes direction dependence in the theory as well as unconventional energy dependence that introduces novel effects, including Lorentz violating neutrino oscillations and modifications to the dispersion relations of different particle species, which naturally could make particles move faster than light. In some models of broken Lorentz symmetry, it is postulated that the symmetry is still built into the most fundamental laws of physics, but that spontaneous symmetry breaking of Lorentz invariance shortly after the Big Bang could have left a relic field throughout the universe which causes particles to behave differently depending on their velocity relative to the field. However, there are also some models where Lorentz symmetry is broken in a more fundamental way. If Lorentz symmetry can cease to be a fundamental symmetry at Planck scale or at some other fundamental scale, it is conceivable that particles with a critical speed different from the speed of light be the ultimate constituents of matter. In current models of Lorentz symmetry violation, the phenomenological parameters are expected to be energy dependent. Therefore, as widely recognized, existing low-energy bounds cannot be applied to high-energy phenomena. However, many searches for Lorentz violation at high energies have been carried out using the Standard Model extension. Lorentz symmetry violation is expected to become stronger as one gets closer to the fundamental scale. Another recent theory resulting from the analysis of an Epr communication setup, has the simple device based on removing the effective retarded time terms in the Lorentz transform to yield a preferred absolute reference frame. This frame cannot be used to do physics but it provides an objective, absolute frame all could agree upon, if superluminal communication is possible. If this sounds indulgent, it allows simultaneity, absolute space and time and a deterministic universe whilst the status quo permits time travel causality paradoxes, subjectivity in the measurement process and multiple universes. Superfluid theories of physical vacuum. In this approach the physical vacuum is viewed as the quantum superfluid which is essentially non-relativistic whereas the Lorentz symmetry is not an exact symmetry of nature but rather the approximate description valid only for the small fluctuations of the superfluid background. Within the framework of the approach a theory was proposed in which the physical vacuum is conjectured to be the quantum Bose liquid whose ground state wave function is described by the logarithmic Schur-paragraph-Dingo equation. It was shown that the relativistic gravitational interaction arises as the small amplitude collective excitation mode whereas relativistic elementary particles can be described by the particle-like modes in the limit of low momenta. The important fact is that at very high velocities the behavior of the particle-like modes becomes distinct from the relativistic one, they can reach the speed of light limit at finite energy. Also the faster-than-light propagation is possible without requiring moving objects to have imaginary mass. Time of flight of neutrinos, MINOS experiment. In 2007, MINOS collaboration reported results measuring the flight time of 3 GeV neutrinos yielding a speed exceeding that of light by 1.8 sigma significance. However, those measurements were considered to be statistically consistent with neutrinos traveling at the speed of light. After the detectors for the project were upgraded in 2012, MINOS corrected their initial result and found agreement with the speed of light. Further measurements are going to be conducted. Epr neutrino anomaly. On September 22, 2011, a paper from the Epr collaboration indicated detection of 17 and 28 GeV muon neutrinos, sent 730 km from CERN near Geneva, Switzerland to the Gran Sasso National Laboratory in Italy, traveling faster than light by a factor of 2.48 a, 10 of 5, a statistic with 6.0 sigma significance. On November 18, 2011, a second follow-up experiment by Epr scientists confirmed their initial results. However, scientists were skeptical about the results of these experiments, the significance of which was disputed. In March 2012, the Icarus collaboration failed to reproduce the Epr results with their equipment, detecting neutrino travel time from CERN to the Gran Sasso National Laboratory indistinguishable from the speed of light. Later the Epr team reported 2 flaws in their equipment setup that had caused errors far outside their original confidence interval, a fiber optic cable attached improperly, which caused the apparently faster-than-light measurements, and a clock oscillator ticking too fast. Tachyons. In special relativity, it is impossible to accelerate an object to the speed of light, or for a massive object to move at the speed of light. However, it might be possible for an object to exist which always moves faster than light. The hypothetical elementary particles with this property are called tachyonic particles. Attempts to quantize them failed to produce faster-than-light particles, and instead illustrated that their presence leads to an instability. Various theorists have suggested that the neutrino might have a tachyonic nature, while others have disputed the possibility. General relativity. General relativity was developed after special relativity to include concepts like gravity. It maintains the principle that no object can accelerate to the speed of light in the reference frame of any coincident observer. However, it permits distortions in spacetime that allow an object to move faster than light from the point of view of a distant observer. One such distortion is the Alcubierre drive, which can be thought of as producing a ripple in spacetime that carries an object along with it. Another possible system is the wormhole, which connects 2 distant locations as though by a shortcut. Both distortions would need to create a very strong curvature in a highly localized region of spacetime and their gravity fields would be immense. To counteract the unstable nature, and prevent the distortions from collapsing under their own weight, one would need to introduce hypothetical exotic matter or negative energy. General relativity also recognizes that any means of faster-than-light travel could also be used for time travel. This raises problems with causality. Many physicists believe that the above phenomena are impossible and that future theories of gravity will prohibit them. One theory states that stable wormholes are possible, but that any attempt to use a network of wormholes to violate causality would result in their decay. In string theory, Eric G. Gaiman and P.E.T. Aho unregistered trademark Ava have argued that in a supersymmetric 5-dimensional GAR paragraph del universe, quantum corrections to general relativity effectively cut off regions of spacetime with causality violating closed time-like curves. In particular, in the quantum theory a smeared supertube is present that cuts the spacetime in such a way that, although in the full spacetime a closed time-like curve passed through every point, no complete curves exist on the interior region bounded by the tube. Variable speed of light. In conventional physics, the speed of light in a vacuum is assumed to be a constant. However, theories exist which postulate that the speed of light is not a constant. The interpretation of this statement is as follows. The speed of light is a dimensional quantity and so, as has been emphasized in this context by Joe Pound Omaguajo, it cannot be measured. Measurable quantities in physics are, without exception, dimensionless, although they are often constructed as ratios of dimensional quantities. For example, when the height of a mountain is measured, what is really measured is the ratio of its height to the length of a meter stick. The conventional SI system of units is based on 7 basic dimensional quantities, namely distance, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. These units are defined to be independent and so cannot be described in terms of each other. As an alternative to using a particular system of units, one can reduce all measurements to dimensionless quantities expressed in terms of ratios between the quantities being measured and various fundamental constants such as Newton's constant, the speed of light and Planck's constant. Physicists can define at least 26 dimensionless constants which can be expressed in terms of these sorts of ratios and which are currently thought to be independent of one another. By manipulating the basic dimensional constants one can also construct the Planck time, Planck length and Planck energy which make a good system of units for expressing dimensional measurements, known as Planck units. Maguijo's proposal used a different set of units, a choice which he justifies with the claim that some equations will be simpler in these new units. In the new units he fixes the fine structure constant, a quantity which some people, using units in which the speed of light is fixed, have claimed is time-dependent. Thus in the system of units in which the fine structure constant is fixed, the observational claim is that the speed of light is time-dependent. While it may be mathematically possible to construct such a system, it is not clear what additional explanatory power or physical insight such a system would provide, assuming that it does indeed accord with existing empirical data. See also Science fiction, notes. References, Fowler, D.F. Floyd, M.J. Superluminal Motion in Astronomy. European Journal of Physics 23, 69/81. Bibcode, 2002 EJPH. 23. 69 FDOI, 10.1088233110 Kaku, Michio. Faster Than Light. Physics of the Impossible. Allen Lane PPA 197/215. ISBN A978-0-7139-9992-1 NIMS, GAR 1/4 NTER. Zero Time Space. Wiley VCH. ISBN A978-3-527-40735-4 Kramer, J. G. Faster Than Light Implications of Quantum Entanglement and Non-Locality. In Millis, M. G. al. Frontiers of Propulsion Science. American Institute of Aeronautics and Astronautics PPA 509/529. ISBN A1-56347-956-7 External links, scientific links, measurement of the neutrino velocity with the Epr detector and the CNGS beam, Encyclopedia of Laser Physics and Technology on Superluminal Transmission, with more details on phase and group velocity, and on causality, July 22, 1997, The New York Times Company, Signal travels farther and faster than light far apart, two particles respond faster than light archives, Marcus Parr paragraph cell, faster than light speeds in tunneling experiments, an annotated bibliography, Alcubierre, Miguel. The Warp Drive, Hyperfast Travel Within General Relativity, Classical and Quantum Gravity 11, L73/L77, A Systemized View of Superluminal Wave Propagation, Relativity and FTL Travel FAQ, Usenet Physics FAQ, Is FTL travel or communication possible? Superluminal, Relativity, FTL and Causality, Superluminal Velocity Fusing with Einstein Special Relativity, Stimulated Generation of Superluminal Light Pulses via Four-Wave Mixing DOI, 10.1103/Phys Rev Let 108.173902, Proposed FTL Methods Links, Conical and Paraboloidal Superluminal Particle Accelerators, Relativity and FTL Travel Homepage.